Okay, let's start recording. So this week we're going to be talking about shear, and in this workshop I'm going to run through shear failure theories, right? So telling you about how they find the shear capacity of reinforced concrete beams and what like the history kind of was leading up to our modern design philosophy, which is in the Australian standards AS 3600. And then followed by calculating two types of questions. The first type is the shear capacity. So if you remember from week 5, right? In week 5, we did flexural capacity, or let's call it ultimate stage 3 flexure capacity, right? Where you had to work out phi mu, right? So that was week 5, the flexure topic, right? In week 7, we did flexural design. And in flexural design, you might remember it was a lot more of an iterative process. In other words, wait, let me just check my recording. Yeah, yes, okay. In week 7, it was a lot more of an iterative process. In other words, we didn't know the size of the beam that we were designing, and we didn't know the amount of reinforcement that was going into it. So there was multiple moving parts as we were doing the question, right? So today's workshop will be focused on shear, right? And the two types of questions I'm going to show you, the first being more similar to the week 5 topic, where we were just determining the capacity of something, provided we knew what like the setup looked like in terms of how much, what's going on here? In terms of how much steel we had, the size of the concrete beam, etc. And then the second part of the workshop after the break, we'll be doing shear design. So that will be more similar to what you saw last week, except instead of flexural design, we're doing shear design, all right? Okay, so just to recap on the content. So we've done week 5 was flexural capacity, week 7 was flexural design. The good news for you guys is if you found week 5 and week 7 hard, that's the hardest it gets in this course, okay, in terms of jump in difficulty. Now we're gonna like go back to flexural capacity once we reach week 10 in terms of columns. So it's still good to know the flexural theory, but the jump in difficulty won't be as high as what you saw in week 5, all right? And then in week 9, so next week, you're going to see some other flexure topics come up again. If you remember with flexure, we had the 3 stages. We had the uncracked stage, the cracked stage, and the ultimate stage, right? The third one relates to week 10 columns, and the first 2 relate to serviceability, which you're going to start to see next week. The good news about this week is that we're taking a step back from both of them in terms of the methods that we're going to use to solve it. And what you'll find is that designing for shear is actually probably the easiest topic, okay? And what you'll find in your final exam is you're going to have 6 questions most likely, right? So Q1 to 3 are related to the first part of the course, right? I'm talking about these first few weeks, right? So that's to do with cement chemistry, okay? And then you're going to find that there's going to be there's going to be 3 more questions, and this is to do with the second half of the course. So this is worth 80% of your exam, whereas the first part is only going to be worth 20%. So these are short questions. These are your long response questions, right? And for this, it can basically be, it's pretty much always a flexure question, right? So either week 5 or week 7. And then question 5, it's a 50% chance of being shear and a 50% chance to be serviceability. Okay, and then, oh, actually, you know what? Sorry. These last 3 topics, it's 2 of them. So 3 choose 2. Okay, so whatever probability that is. The thing is, if you get a shear question in your finals, you should be very happy because it's relatively easy compared to the other topics, all right? So that's all just to preface that this workshop will be, hopefully, a breath of fresh air, all right? Do you guys have any questions about that? Fantastic. All right, So let's talk about shear failure theories, right? So I know I just started the workshop saying that everything you're going to see is super easy, but what I'm going to tell you is the theory behind what you're doing is actually relatively hard. In fact, people specialize in reinforced concrete, specifically looking at shear failure. Okay, this is like quite an advanced topic actually, and I'm not going to be an expert at it. I'll tell you what I do know though, and try to pass on that knowledge. But the theory is hard, but the methods are easy. Okay, so what you actually see when we go through the questions will be relatively easy. Okay, so, but let's go through the theory anyway, because it's still good to know, right? Okay, so very simply, what is shear? Okay, shear is talking about the forces perpendicular to your beam's longitudinal axis, right? So if your beam, right, has a longitudinal direction running that way, we're talking about, in this particular instance, the vertical shear. Okay, so any perpendicular forces applied to the beam, right? So when you have a frame, a concrete frame that looks like this, right? You've got your beam member and it's attached to your columns, okay? So let me just quickly talk about this in a little bit more detail. So you have something that looks like this, right? This is just, I'm not drawing the bottom of the columns, but this is kind of roughly what it would look like in terms of the connection detail, right, between the beam and the column. The question is, this is a real life system, so your beam has like thickness and same with the columns and stuff like that. The question is, how would we model it mathematically, right? So one school of thought, right, even though this system, we know it's simply supported in some way. In other words, it's got two supports, right, at the columns. How would you model the beam? Okay, so we're focusing on the beam. One school of thought is you can model it as simply supported with pin supports. And another school of thought is you can model it as fully rigid. Okay, so what is the difference between these kind of supports and these kind of supports? The main difference is the rotational stiffness, right? So rotational stiffness, let's just say, for the sake of putting numbers here, that we have 0 rotational stiffness when we have pin supports. In other words, it doesn't resist the bending moments whatsoever. So you would see a bending moment diagram that looks something like this, right? Given vertical loading. Just imagine there was a UDL there, okay? The other school of thought is you've got 100% rotational stiffness, and these are modeled as fixed supports, right? In which case, your supports will absorb moment, and there'll be significant negative moment at the support, right? Okay, in reality, a lot of systems look more like this, even though it's less intuitive. This is a coil, right? And this is what we call a rotational spring support. Rotational spring support. And this can be a range of kind of stiffnesses, right? Somewhere in between 100% and 0% stiffness, okay? And honestly, you don't need to know that much, except that it will be somewhere in between these two things in reality. So I guess, yeah, you have to consider some negative moment, maybe not as much as if this was fully rotationally stiff. But yeah, anyway, that's what I'm trying to tell you. This connection detail will have some kind of negative moment, all right? So with all that said, if we were to draw the bending moment diagram over these cracks, right? Or sorry, over this beam, which is cracked, you'll find that there'll be flexural cracks, right? At the middle of the beam on the tension side, because we know that the concrete's pulling apart and wants to crack, right? And the location which has the highest bending, which is the middle, is where you'll see the flexural cracks appear, right? Okay, but what if we focus instead on the shear force diagram, which might look something like this, right? Okay, pretend I drew that evenly. So, in fact, the max shear force is at the support, right? However, what you'll find is that the shear cracks actually appear some distance away from the column, okay? And that's because essentially the column will provide a local spot with high amount of shear capacity. Another way you can think of it is that the UDL, which is applied on this portion, goes directly into the column as axial force. So it's not really taking shear necessarily in that location. It's more like a bearing kind of effect, right? So transverse compression. So that's all to say, we know that some distance away from the middle of that column is where shear cracks will appear, okay? And these shear cracks, we're gonna say, is DO away from the middle of the column, and DO is the depth to the outermost steel, okay? So this is the cross section of your beam, and you can either have one or more layers of tensile steel. DO is referring to the depth from the compressive face to the outermost tensile steel layer, okay? But if you only have one layer of tensile steel, it's just the same as the effective depth, basically, right? Okay, so we're saying that this dimension is projected horizontally and will inform you where the shear cracks will appear. Okay, so that's the code provisions, basically. Do you guys have any questions about that? Okay, so nothing's too difficult so far, except it's going to get more and more complicated before it gets easier. So basically, in the early days, they essentially used something called a truss analogy to represent the stress fields within a reinforced concrete member. Okay, so what does that mean? Basically, a concrete beam is taking in reality, a concrete beam is taking shear and bending, right? But we're gonna pretend that there is like a truss system within this reinforced concrete beam made up of steel and parts of it are concrete, okay? So we're going to use an analogy to say that parts of the system are in compression and parts of it are in tension. So if I draw your attention to these different types of bridges, right, you've got your Warren truss and Pratt truss and Howe truss, and what you'll realize is that blue is representing compression here. The top chord of all of these bridge types are in compression, and the bottom are all in tension. Where they are different are in the diagonal and vertical members. Okay, so the closest representation we have is a Howe truss, where we've got vertical tension ties, okay, and diagonal compression struts, okay. So this is basically how we represent a reinforced concrete beam, right? I'm trying to find the right order to say everything in. Okay, so there you can see it in terms of, you've got the longitudinal bits of steel, right? So if I drew this sideways, rather a cross section of it, let's say we're cutting there. The longitudinal reinforcement up here is in compression, and the longitudinal reinforcement down here is in tension. And what we're saying is that the stirrups, or the shear reinforcement, act as vertical tension members, right? Holding up the concrete beam, okay? And what we're saying is that we have these diagonal concrete struts, right, acting in compression, because we know that the concrete can take on compression but not tension. So these are how the two materials are interacting with each other in a truss-like manner, okay? And yeah, that's just a recap of what I was saying. Let's do a quick recap on how internal forces work, all right? So you may or may not have learned this properly in Eng 1300, but if you recall back to Eng 1300 where we're looking at internal forces, what you'll find is, I'll give you guys some example numbers. You got a simply supported beam, and you've got a uniformly distributed load like so. Let's say that has 2 kilonewtons per meter applied as a UDL, and we've got some kind of reaction at these supports. And then the length, let's just say that's 3 meters, right? So we know that the total downwards force has to be counterbalanced by reactions, right? And in this case, because of the symmetry, half of the downwards load is going to go into one support and the other half is going to go into the other support, right? So we know that there's going to be 6 kilonewtons of equivalent force, right, from the UDL. That's going to be applied in the middle. And that 6 kilonewtons is going to be spread into the reactions half and half, like so, right? Okay, if I was to slice the beam in half, right, what happens is if I redraw this, let's say I copy this over, like so, delete a bit of it, like so, la-di-da, give me 1 sec. So this is 2 kilonewtons per meter still, and then this reaction stays like so, and that's some portion of the beam, right? So what I'm trying to say is the overall system is balanced in equilibrium. In other words, we know that the beam's not moving, right? However, if we slice it, you can see that it's imbalanced, right? Because there would be more upwards pushing load than there would be downwards facing load, right? The way that the beam naturally equilibrates the forces is through internal forces, okay? So internal forces. And when I say that, I'm talking about shear and bending, right? So you've got some portion of it that's, so there's an internal shear force and there's an internal bending moment, right? That counterbalances everything such that the whole system is in equilibrium in terms of the moment and the forces, right? The vertical forces, okay? So let me just move that to the side. Okay, now one trick that we can do, right? If I draw the beam's actual thickness, right, the depth, like so, instead of bending moment like the way that we see it here, imagine instead that I drew the steel, right, the compression and tensile steel, and that internal moment can be turned into a force moment couple, okay? In other words, compression and tension, right? So now we can delete the internal moment, and we're now representing it in terms of the compression, like the top chord is taking compression axially, and the bottom chord is taking tension axially. Does that make sense? So that's kind of what we've actually been doing. It's just hidden away from you, right? So we have to basically figure out the internal shear capacity, which I'll tell you how to do in a second. But that's kind of where all these internal forces come from, right? Okay. So building on from the truss analogy. So the truss analogy is essentially based on the fact that these, we call them concrete compression struts, inclined at an angle of 45 degrees from the horizontal. But there's theories, compression field theory, and then later modified compression field theory, which is basically saying we know this isn't always the case, right? You'll find that that angle of inclination is actually closer to 36 degrees rather than 45 degrees. That's one. And secondly, that, let me go back to here, that instead of there being only one diagonal strut per tension tie, or other way around, only one tension tie per diagonal strut, in reality, these diagonal struts actually cross over multiple stirrups or multiple tension ties, okay? So we need something which tells us how to space these stirrups accordingly, right? So these stirrups, right, we're gonna call that spacing S between each of these stirrups, right? And also I'm gonna try to familiarize you guys with the terminology that I'm gonna use, right? So in this lesson, I'm gonna say stirrups a lot. I'm also gonna say transverse reinforcement a lot. I'm also going to say shear reinforcement a lot. ligatures, ligs, fitments, they're all the same thing, okay? It just depends which part of the world you're talking about, okay? In Australia, unfortunately, we use a combination of all of these. In America, they call them stirrups. In like Britain, they use fitments, I believe. Okay, so they're all the same thing, right? Okay, that's what I was trying to say earlier with the internal couple. Okay, so what you'll find is the way that we calculate the contribution of shear strength due to the steel is using this big ass formula, except I'm going to try to explain where this formula comes from as briefly as I can. Okay, so you're going to need to bear with me. I'm going to do another analogy. Okay, so I'm going to copy a bunch of houses over, right, like so. All right, pretend you run a demolition company and your boss tells you that we've got a skyscraper we want to build, all right, and we know this skyscraper's height. Let's say that skyscraper's height is dV, okay? What we're going to do is we're going to demolish houses which are in the shadow of the skyscraper, okay? And there's ways that we can find out the shadow angle, right? The angle which the shadow is cast. Let's call that angle theta V, okay? So this is going somewhere, trust me. All right. So there's formulas to determine theta V. Let's say we know what theta V is and we know what dV is, okay? What I'm interested in is how many houses do I need to demolish, right? How many houses will be 3, 4, etc. Where we know what the spacing of these houses are. Let's say the spacing of these houses is 100 for the sake of argument of whatever unit. And give me one sec. What I want to do first is I want to figure out the horizontal projection of the shadow. Okay, so let's just say from the middle to over here. I want to know how far this shadow is cast, right? And you can figure this out geometrically through this number we're going to call x, right? So we're trying to say that x is equal to the height multiplied by cot, right? Cot theta v, okay? So that's what they do first in this formula. They figure out this variable called x, which is the horizontal projection of this quote-unquote shadow, okay? And again, I'm trying to find the number of houses which I need to demolish, right? We know the spacing of the houses, and we also know distance x, okay? So the way that we find the number of houses, let's just call it n, is we go this. N is equal to the horizontal projection divided by the spacing. Okay, so that gives you the number of houses you're going to demolish. Okay, let's get rid of this analogy. What I'm trying to say is the number of stirrups crossing a cracked bit of the number of stirrups per diagonal strut of concrete. Okay, that's ultimately what the formula is getting at. Okay. Yeah, does that kind of make sense? Anyway, you'll see this formula in action later, but that's kind of where this formula comes from. It's just rearranging geometry until it makes sense. All right, but that's going to be how they find the contribution of strength, of shear strength due to the steel. Okay. All right, let's continue. All right, this is going to be a case of me scrolling till, what's this page? Page 8. I'll go to page 8. Maybe it's page 7. Oh, come on. Okay, basically on the left-hand side screen, you're going to see the shear capacity notes that I've got, and then on the right screen, we're going to run through questions. All right, so the good news for you guys is this, the shear topic is very much a flow chart. Okay, you just do one thing, you do the next thing, you do the next thing, and it's super straightforward. Okay, in week 5 and 7, you might have been like overwhelmed a little bit because you need to derive the equations and everything for each individual beam section. The good news for you guys is this is very much just plug in numbers and you get the right answer. Okay. All right, so let's see this in action. So first, we're going to determine the ultimate capacity, the ultimate shear capacity of this beam. okay? So this cross section is given to you. You're given the size, okay? And you're given the amount of reinforcement, both the tensile reinforcement, which will come up later, as well as the shear reinforcement. So we call the area of shear reinforcement ASV, right? So that's area of steel in shear. Okay, some other things we need, right, which this question provides us, is the bending moment and shear, and these are at the critical shear failure location, okay? So I'll explain what that means later, because it'll come up in the second question that we run through, okay? But just for now, we're just given these as numbers, all right? We don't need to think more about it. We're also given some material properties such as the stiffness of the steel, the compressive strength of the concrete, as well as the yield strength of the tensile steel and the shear bars, okay? So that's 500 and 500. And we're also given the max aggregate size, but I don't think we use that in this question. Okay, so let's go through everything step by step. Okay, so looking on the left screen, one thing which I forgot to point out before, to find like the total shear capacity of a reinforced concrete beam is like it's in two parts, right? The first part is the contribution due to the concrete without any steel, and then the other part is what the steel contributes to the strength as well. Okay, so the notation is VUC added to VUS. Okay, so step one, what we want to do is we want to find VUC. So we want to find what the contribution of just the concrete does for our shear strength. Okay, so that comes with this formula, and what you'll see is little bubbles that I've put there, like 1, 2, and 4. I'll explain why there's not a 3 there in a bit. And that's the order which we want to solve everything in, okay? So it's because of dependencies, right? So if you try to launch in and solve KV, right, which is step 4, or bubble 4, you're not going to be able to solve it without dV, I think. So anyway, just go BV, dV, and then KV, all right? So we know what BV is, okay? So BV stands for the shear width of the beam, okay? So in our particular question, we have a rectangular beam, but if you had a T-beam, this is a different value, right? Well, it's not a different value, but it's the web width, okay? So for the case of a rectangle, BV is the same as the width, okay? So it's just the width of your section. Whereas BV for a T-beam is the web width, okay? In our particular question, we're going to do this situation. So that's just going to be 400 based on what they gave us in the question. Okay, next thing we need to do is, I'm going to get rid of that for a moment. Next thing we need to do is find dV. Okay, so dV is your internal lever arm. Okay, and it's the max between these two numbers, right? So the first number, oh, sorry, I'm going to swap this around because in my notes it's the other way around, I believe. Okay, sorry, so it's a max between 72% of your overall depth and 0.9 of your effective depth, right? So just to recap, here's our steel, right? This isn't drawn to scale. The effective depth, lowercase d, is 735, right? The overall depth, right, capital D, is 735 added on to 65, so it's going to be 800. Okay, so what we're saying with dV is that you take 72% of your overall depth, right? So that gives you, sorry. Oh, I didn't calculate the actual numbers, okay, but anyway, so yeah, you calculate these two things, right? You're going to substitute in 800, and little d, you're going to substitute in 735, right? And you find the maximum between those two things, okay? And in our case, it's 661, right? So that's the value we take for dV. So I like to think of it like, pretend that's the center of your compressive forces. I'm going to try to draw like that, right? So that's talking about the contribution of the compressive steel, as well as the portion of concrete which is acting as your compression block, right? That's just the center of it, right? And so from the center of that to your steel, that's dV, okay? That's your internal lever arm for your moment couple, okay? And this is just a empirical formula, so it makes it a lot easier than trying to do it by doing some weird like force equilibrium stuff, okay? Moment equilibrium stuff. Okay, cool. So that's dV. Now we've gotten dV. Okay, the thing is, next we're gonna try to work out kV. So kV is your aggregate interlock factor. I'm gonna scroll down on the left-hand side here. Okay, kV is your aggregate. kV is your aggregate interlock factor. Okay, and there's gonna be two ways you can solve it, right? The first way is the simplified method. I'm just gonna call it the simple method, and the second way is the detailed method. Okay, and in this question, it says use the detailed method and the simplified method to solve this question, right? In your final exam, just check whether they're asking for the simplified method or the detailed method, all right? So in the simplified method, you can go directly from, sorry, you can directly solve it, right? So you just go step 4, kV is whatever, okay? In the detailed method, you actually need to find epsilon x first before you find kV. Okay, so that's where that bubble 3 comes from. It's only a part of the detailed steps, all right? So what I'm gonna do is I'm gonna do the simplified method first, right? Where we can directly solve for kV. So in the simplified method, if you look at the left-hand screen, it says kV depends on if ASV on S is greater than ASV min on S, right? Which has a formula. And that formula is what you can see here, right? So, okay, what does this actually mean? Let me just quickly draw a beam out, right? So, la-di-da, I've got a beam, something like this. And let's just say we've got some stirrups, right? I'm just going to duplicate that a few times. Okay. The first thing is, well, what is ASV? Okay, so ASV is basically, if I draw, actually, you know what? I'm just going to use this cross section. So we know what ASV is in this particular question, but I want you to be able to visualize what ASV is, right? So if I take a cut across the middle of our beam, right? Think about how much shear area we're cutting through, okay? So each of these bars, right, has an individual area of 110 millimeters squared, right? So if our cuts across 2 legs of transverse reinforcement, that means that ASV is 2 times 110, right? Okay. So what ASV on S means is, this is ASV, sorry. So ASV is 2 legs per stirrup, okay? And then S is referring to the spacing of these transverse bars, okay? Because the individual area of a single like transverse bar doesn't really mean anything. What matters in the grand scheme of the entire length of the beam is this the area divided by the spacing. So sometimes I'll refer to this as the transverse steel density. Okay, density referring to what is that area of the bar divided by the spacing. Okay, so I'll give you an example why that matters. If I half the spacing, right, but I keep it as the same area, so now spacing has become halved. That means I've got twice as much reinforcement in my overall beam, right? So when you have a higher density by halving the spacing, that's what really matters, okay? So the ratio of ASV to the spacing. Does that make sense? I feel like it doesn't make sense to some people. Is it okay? Okay, all right. And likewise, right, just building on that, if we had that original scenario and I doubled the spacing for whatever reason, right? So I doubled the spacing. I have half as much reinforcement overall over the entire length of the beam as I did before, right? So therefore the transverse steel density goes down. Okay, so I want you to think of everything in terms, when you see A as V on S, I want you to think of it in terms of density over the entire length of the beam. All right. Okay. Cool. So next, if we plug in these values, right? So we're given in the question that ASV was 220, and we're told in the question as well that the spacing is 250 mil. Then we know this ratio, okay? We know the density is 0.88, right? Okay, and then ASV min on S has a formula, and this is the formula, all right? And so what we can do is we can plug in F-C, we can plug in BV, so this was from step 1, right? And we can plug in FSY.F. Okay, so this might look a little different to what you saw in the question. The question said FSY for the N10s, which are the stirrups, and the N24s is equal to 500, okay? So you might be wondering, what the hell is FSY.F? FSY.F just stands for the yield strength of the bars when used as a fitment. And remember, fitment's the British word for stirrups, okay? So that's why we use a combination of everything. Anyway, stupid. All right, so once we do this calculation in our calculator, we get that the minimum, so this is the minimum density that's permitted, right? The minimum density is 0.36, right? So we know that our steel density that we've provided is greater than the minimum steel density, right? And so if that's the case, if I scroll down on my notes, which are on the left, okay. If that's the case, right, so in the top scenario that you can see on the left there, KV is simply 0.15, okay, simple method, easy as, all right. So now we can put in all our values to find the shear strength of the concrete. Okay, so for KV, we plug in 0.15. For BV, we plug in 400. For DV, we plug in 661. And for F-C, we plug in 32 MPa, giving us this value for the shear strength of the concrete, okay? All right, so if we were to do that except using the detailed method, here's how it would go. All right, I'm going to flip this page. Okay, so as I mentioned before, in order to find KV, we need to find epsilon x first. Okay, so what's epsilon x? Right, so if I scroll down on my notes, basically, if you think of a beam and bending, right, and I was to map the strain, right, we know that the neutral axis, right, for stage 3 bending is going to be above the middle somewhere, right? So that's the neutral axis. And what we're interested in actually is what the strain is at the mid depth, okay? So mid depth referring to d/2, all right? So we're going to call that epsilon x, the longitudinal strain at the mid depth of our concrete section. And so we can find that provided we know these things, or we can approximate it, provided we know these things, all right? So we need to know what the bending moment is, and the shear, and the, what's this called? Internal lever arm. Okay, so that's from step 2, remember? All right. Okay, so we know these things, so that's good. We can plug them in. So M star was given to us in the question. It was 350 kilonewton meters, except we're not allowed to use kilonewton meters in this expression because we might get the wrong answer. So I want you to keep in mind, for this particular expression, it's useful to keep all the units with this set of units, I guess, right? So you want to keep everything in newtons, millimeters, and MPa. All right, so for our particular scenario, we want to convert from kilonewton meters to Newton millimeters, right? How do we do that? We need to multiply by 10 to the 6. Okay. So we go 350 times 10 to the 6th, and that gives us an answer in Newton millimeters, all right? dV was given to us, it's 661, and that's already in millimeters. And for shear, we go 300, which was in kilonewtons, and so we have to multiply that by 10 to the 3 in order to get it in newtons. All right. ES is the elastic modulus of the steel, which I think they might have given us that in GPa. So remember, if it says 200 GPa, that's the same thing as saying 200,000 MPa. All right. Okay, AST is the area of tensile steel. That's governed by flexural design, but for this question, it's actually given to us already. Okay, so AST was provided to us. It was 1800 millimeters squared. Okay, so once you punch all of that into the calculator, you get 0.00115. Okay, so this is the max value it can be. It can't be bigger than 0.003, but our number is not going to be anywhere close to that. Okay, great. So that's the value we're going to use. And so if I scroll down on my notes, again, just like in the simplified method, kV is going to depend on whether your transverse steel density that you've provided is greater than the minimum, right? But we actually already calculated all that in the previous part where we were calculating the when we're doing for the simplified method, right? So that's all this, right? So we know that 0.88 is greater than 0.36, right? So if we were to do this question in this order, we don't need to prove this because we knew this is true already from the simplified method, right? So therefore, we're going to use kV. We're going to use this formula. And this formula is different to the previous formula because this is the detailed methods formula, right? And so here's why we needed epsilon x as an intermediate step, all right? It's because in the detailed method, we need to plug in epsilon x into kV, okay? Giving us kV value of 0.147. Okay, so remember with the simplified method, we had kV is 0.15. Here, it's only slightly different, right? But that's the difference between the simplified and detailed method for this particular step. Okay, so there's going to be a different step later, which is going to be different for the simplified and detailed method as well. Okay, so now we can plug everything in just like before. And the only thing that's going to be different is the value for kV. So BV is going to look familiar from when we're calculating it for the simplified method. And dV is going to look similar as well, and F-C doesn't change either. Okay, so that's the only thing that changed, and this value is only slightly different, right? So this is the VUC if we calculated it using the detailed method, right? Okay, that was step one. All right, so next step is finding the strength of the steel, right? The stirrups. So again, we're going to do simplified method first before doing the detailed method. Okay, so the simplified method, essentially, it tells you that your inclination angle for your compression strut is 36 degrees, right? And that's just a flat number. Okay, so that's the simplified method, nice and easy. And we're going to use that and plug it into this expression, right? So this expression, this expression comes from, one sec. It comes from all the shit I was trying to explain earlier, right? Like the shadow and the skyscraper and the houses and all that crap, okay? So that's where it comes from. But the good news for you is you don't need to do that skyscraper geometric calculation every single time. You just plug in this formula, okay? So ASV is 220. dV, we calculated earlier, is 661. FSY.F is 500. And the spacing is 250, okay? And here, with the simplified method, we're simply going to plug in theta V as 36 degrees, and that's it. Keep in mind, when you see cotangent in these formulas, right, it's just 1 over tan, right, on your calculator, because you can't type cot on your calculator, but you can type the fraction 1 over tan, right? Okay. that gives 400.6 kilonewtons as our answer. Okay, so the only difference, right, is for the detail method, it's just going to require one extra step. Instead of assuming that the inclination angle is 36 degrees, we plug in epsilon x. All right, so epsilon x we calculated earlier was this. And you get an answer which is in degrees when you do this, okay? So the answer is 37.1 instead of 36, right? So all these other things stay the same, except we plug in 37.1 degrees here into cotangent. All right, that's the only difference. And that gives us 384.6 kilonewtons, all right? So this answer is only slightly different, again, from if we use the simplified method. All right, so now the final thing we're going to do is find the total capacity, right? So the way that we find the total capacity is we know that VU, being the shear capacity of the beam, is broken up into the concrete component and the steel component, right? And then we're going to multiply the whole thing by phi, which is the capacity reduction factor. So unlike in the flexure topic where phi can be a range of numbers, you know, in the flexure topic, phi could be between 0.85 and 0.65. In this topic, phi is just 0.75, so nice and easy. Okay. All right. So we can plug in these values. So VUC using the simplified method was 224.4. VUS using the simplified method was 400.6. And that gives us this as the capacity, right? So this is already factored. Oh, sorry, as in once you multiply this by 0.75, this answer is your factored capacity, okay? So that's for simplified method. For detailed method, I don't know why that's there. Okay, we got different numbers for VUC and VUS. Okay, so VUC was 219.9 and VUS was 384.6. So what you'll find is that in fact the detail method gave you a lower number, a more conservative number for your capacity actually in this particular question. Okay, any questions so far? Yes.
So in exam, you have to do both methods, or?
The exam will just say use a simplified method, and you go to simplified method, or it'll say use the detailed method, and you do the detailed method. I think from memory, it's always the simplified method in exams, but I wouldn't risk it. Okay, so in your workshop questions, there'll be a mix of simplified methods and detailed methods. All right, learn both, but if I was to put money on it, it's going to be simplified method in your finals. Just because there's other stuff they want to test you on, probably. Okay. All right, I'll give you guys a break. QR code's going to be on the left. Break. Let's do 5 minutes. All right. Break until 2:05. All right. You guys have any questions? Anything? You guys have any questions? Yes. The simplified method just says the angle doesn't deviate that much. That's it. Full stop. Yes. So, yeah. You just want to see American flag dots. Actually, what? You just made 10 minutes. The question might tell you the yield strength in 2 different ways. The first way they might tell you is how they told you at first y for n10s and n24s. This is equal to 500.
it's
Oh,
like
is it just the workshop stuff? The answers would be
So therefore,
that's what's from this one's funny workshop.
because the other way that I should tell you is like this y equals that equals y not. So sometimes they'll tell you like or
The drawing that's just been nice.
to be like one number equals y not. This might be like 哦，其实是个。
Yeah, that five shit, that's hard.
This is like, you know when you adjust, like you have the BD less than equal equation, and sometimes you like adjust it, so you have when you, like do you have to do that?
So this isn't the way that works in steels, because in steels it's like iteration 1, do all this, and you do as many iterations as you want to like find the number. The iterations here are unnecessary because you make assumptions, just think about it, like then you refine the number, and then with that refined number, you come to an even more refined number. So there's a set amount of iterations. It'd be like 1, rough guess, 2, a bit more refined, and the third one's refined enough that it's
So you have to.
Whereas steels is like the number of iterations depends on how much you so that was very good. He wins money. This one was assuming that the set will go down. Reverse game. So you know when you get you win. That's the hardest part. What's your first thing? So the way that you
With like the.
yeah, they have a but you put in a second page.
So like, when you did it, did you find that you had like a lot of the processing memorized?
Yeah, I would initially. No, actually, the double-sided cheat sheet takes a lot longer than you think to write up. I want to see because it's so dense with money. Oh yeah. Use that as like a preliminary cheat sheet, and then one day before the finals, write up. And then
when you sell out of this price, because now everyone has apples, it loses its value. So when you buy apples, that's the lowest goal. So what do you buy more of the gains value?
Plus you know like you don't need it. For me, I knew like the second half of the course way better than the first half.
Wait.
All the chemistry and like that was
You know what?
That's like 20%.
That's 20% of the
Because technically, he bought it in a position, technically, he's trying to sell
there are some
apples
free
to make money, but everyone just wants
how
apples.
to do that
So
diagram.
it doesn't get
Well, this is memorizing.
So he's trying to sell apples, right? But everyone took his apples.
No, 3 countries okay. 3 countries is what's going on.
Because they wanted to go up.
So like assumptions is like for example like this after it's going to be like oh you assume
The question is to,
I think assumptions like that.
That's
For example like
that's part of the simple plan. I was on stage.
Like we assume these
Just learn either process, the side by method and the detail. And then if the final is just overlap,
it changes the value. and you can literally enter position, and you will earn money. I'll come back to you guys with the other one. So when you enter position, you need to say, I'm going to enter my position, and I want to do that. So that's good. That's what you're So there's 2 types of positions here. Yeah, so you let me know that the team to lose or the team to win. So when you let the team to win, they don't make money.
You can do like what you can do.
Oh, that's true.
Yeah, top and dog.
But like, I like that it was gay.
Yeah, it was.
Because if I had to listen to like people.
Related?
Why?
But like that was a game.
A lot of the time,
I know a lot of people.
Yeah,
say
that's
why.
Right, yeah.
Yeah, that was very funny. That was the funniest part. The song part was very funny. The song part was very funny. When she actually met us. The song was very funny. Yeah, you know, even before I literally said, I was like, oh, yeah, someone's gonna
I know, I was talking to Shear, and I was like, do you know what's funny? I just switched. She was like, yeah, you should do it. I was like,
yeah, that's like big fun. Yeah, I feel like it's super yeah, I just got used to it. I don't know, that was pretty good about it. It's also my spaceship, so you know, so you couldn't see. I don't want to read.
When you're selling, right, you got
So
the people who are
there's a lot.
when you're buying, it's something you wanted to sell.
There's also a question of like,
You did all those questions. You
Okay, let's continue, guys. All right. Settle down. All right, we're gonna continue, all right? All right. So in this half of the workshop, we're gonna do the shear. We're gonna do a full shear design, all right? So let me tell you what that involves. So if you remember from the first question, they told you quite a few things, right? I'm gonna highlight them. They told you the bending moment that we're gonna design for, and they told you the shear that we're gonna design for, right? The other thing that they told you, which you're not always given, is the amount of steel as well as the spacing. Okay, so in this question, what you'll find is we don't know what this is right off the bat, and we don't know what this is, and we don't know what this is, and we don't know what this is. So we're gonna go through some steps to do a full shear design, all right? Usually shear design happens after bending design. Okay, so what I mean by that, bending design means we know what AST is already, right? So we've done our flexural design and we've figured out the longitudinal steel already, okay? And shear design happens after that for a beam. Okay, so full shear design. Essentially, we're trying to figure out whether we need stirrups, and if we do, how much. Okay, so what we do is first we need to figure out the shear that we're going to design with and the moment we're going to design with. So on the left-hand screen, I'm going to scroll over to, oh wait, no, what am I doing? Okay, sorry. So, okay, focus on the right-hand screen, okay? So I'll just give you some example numbers. Here is where we have, we're provided with the distributed dead load and distributed live load, right? And we apply our load combinations of 1.2 and 1.5. And we can find the overall distributed load, right? In this case, it's 400. Okay, what we can do is we can break down these components actually and call this one W star G and this one W star Q. Okay, so W star G, right, is 145, and that's just by multiplying 121 by 1.2. And similarly, WQ is going to be 170 multiplied by 1.5, giving us 255. Okay, so I'll tell you why this is important to split it up in a second, but just keep in mind the individual components are 145 and 255. If you add those together, you get the ultimate distributed load, right, which is 400. Okay, so why is that important? It's important because we're interested in finding something called the shear envelope, right, which is the worst case loading conditions for our beam in shear. Okay, so okay, let me just move a few things around real quick. Okay, so intuitively, right, you would think that the worst shear that we could possibly have is going to be if we get 400, right, which is the ultimate distributed load, and just put it over the entire beam, right, because we know that a shear force diagram that looks like this, right, has the peak shear over here, right? So that's the peak shear, right? But what we need to do is we need to account for the scenario where, sorry, I think I've drawn it down here. We need to account for the scenario where, okay, wait. Let me redraw that. I skipped a step. So you got shear force like this. Okay, the thing is, right, the beam, depending on how you load it, doesn't actually have 0 in the middle in the worst case scenario, right? So when your live load, so your dead loads don't move around, okay? Your dead loads stay in the same spot, but your live loads, right, in fact, they can move around, right? So people, pedestrian traffic can move around, things like that. And so this doesn't accurately represent the max shear force that the middle of the beam can experience, right? So how do we represent that as a different loading scenario? How we do that is by applying the live load over only half of the simply supported beam, right? Whereas the dead load stays over the entire portion, right? But if we only apply the live loads over half of the beam, it's telling us that when we do our analysis, the middle of the beam is non-zero, okay? So just to highlight the difference, right? You apply the dead and live load over the entire simply supported beam, and you're going to get the max shear force where the supports are, right? That's still true, but it gives you a 0 shear force in the middle, right? Which is going to be non-conservative if you design like that. So we want to find out the max shear force that the middle of the beam can experience, and the way we do that is by only allowing the live load to be applied on half of the beam at a time. Okay, so what you'll find is that this is the shear force diagram for this particular loading scenario, but and let me flip this real quick. Let me just move this around a bit. One sec. Delete. Okay. This moves like this moves like this, and this one becomes positive. I forgot the negative signs. So that one's negative, that one's negative. Okay. The idea is if we also accounted for the scenario where the live load's applied on the right-hand side of the beam, so let's say the live load's on the right, versus the live load being on the left, right? We have these kind of mirrored shear force diagrams, right? So this top scenario is where the live load's only applied on the right-hand side of the simply supported beam, and it gives you this. And then if the live loads are only applied on the left-hand side, it gives you this. All right. So what you'll notice is that this is the exact same number, 233, right? It's just whether it's positive or negative based on which side that you apply it on, right? Okay. So what does a shear force envelope look like? The supports, right, are going to take the max shear from the very first, from the loading case where your ultimate distributed load is applied over the whole thing. But to find the max shear at the mid-span, it's basically plus or minus that number, okay? The number we found from analyzing the simply supported beam with the live load only applied over half of it, okay? Does that make sense? Okay, so to help you visualize it, right, because someone asked about this in my last class. Oh, actually, this week and next week, you're not my only class. I'm covering for a mate doing a 9 a.m. class on Fridays. Okay, so here's the shear force diagram, right? So our shear force envelope looks something like this, okay? All right, and the first loading case that you saw, right, scenario 1, let's say, is the one in red, okay? Scenario 2, right, which was only applied over half the beam, let's say this one, looks like this. Something like that, okay? And then, what color? Blue. Scenario 3 is the other way around, where it is like that, and then like that. Something like that. Anyway, point is, you can see that the shear force envelope is the peak at the middle and the sides, right? And the envelope is gonna, it's gonna cover all three scenarios, right? Okay, so why is that important? It's important because we're interested in finding the design shear. And the design shear is where you get the shear envelope, right, which is the worst case scenario from all three of those loading cases of the shear force diagram. And you go a distance of DO away from the support. Okay, so as I mentioned before, the reason we do this, right, is because the critical point of failure where the shear cracks appear in your beam is a distance DO away, right? So in that same location is where we're going to take the design shear, okay? Not only is that where we're going to take the design shear, where am I? That's not only where we take the design shear, but it's also where we're going to take the design moment, all right? So when we're doing flexural design, we wanted the peak moment over the entire beam, right? Whereas here, we're interested in the bending moment at the location of, at the design location, right, for shear. Okay, so M star design, M star V. Both of these are when X is equal to DO, okay? X is equal to DO. So that means if X starts at the left-hand side, right, we're moving a distance DO horizontally to here, okay? And that's the location that we're going to take for peak bending and peak shear. Does that make sense? Okay, so you'll see how this works when we do our static analysis, all right? And we're going to follow through with more steps, but I'm going to try, the hardest step to understand is finding the design shear and design moment. So I'll try to spend time explaining that better or more thoroughly. Okay, so all right, that's what we're working towards, right? So on the left-hand screen, we want to create a shear force envelope that looks like that, and then derive a formula to find the design shear, right? And on the right-hand screen is the question that it's presented in, okay? So we're given a bunch of stuff about this question. We're given what the geometry of the beam is. So in our case, we have a T-beam, right? And we're provided with AST already. So we know what the area of the tensile steel should be. we don't know what the arrangement of shear reinforcement will look like quite yet, but we're going to design that later. What we need to do first is we need to find V star design, or V star critical, you can call it, and M star design. And in order to do that, we need to first get a shear force envelope. Okay, so part A and B are just instructions on how to get a shear force envelope. And then part C is about designing the shear reinforcement, this one. Okay, so that's the question that we're presented with. So you can see we're given the length of the beam and we're given the loading on the beam. So first, let's find the ultimate distributed load. Okay, so let me just scroll. Let me flick through my pages until I find the question. One more. Okay, so G. We know that G is 26. We know that Q is 22. All right, so when we factor it, it's 64.2 kilonewtons per meter. Okay, so we know that for the first loading scenario, the max shear is at the support. And luckily for you guys, if it's a simply supported beam, this is just in a simple formula. What this is saying is W star L is the total downwards force on this beam, right? So the equivalent point force. And so each support has a reaction of W star L on 2, okay? And that support reaction is going to be equal to the max shear, right? Which is just the peak shear on the left-hand side here. Okay, so W is 64.2, L is 7.5 meters, and if you divide that by 2, you get 240.8 kilonewtons, okay? All right, the next thing is we now are going to consider a beam where only half of it is live loaded. Yeah, is live loaded. I guess that's one way you can say it. And so what we're doing is we're multiplying WQ by 1.5 in order to turn it into a factored live load. So that's W star Q. And similarly with WG, we're finding W star G by multiplying it by 1.2. Okay, so statics revision, right? What we want to do is we want to take the sum of the moments is equal to 0 around B, right? So we're taking the moment equilibrium, and B is our reference point, okay? We know that AY is going to have a line of action. A line of action is basically a line that extends infinitely in both directions of that arrow, where I've highlighted in green. And then we know that each of these distributed loads has an equivalent point load, right? In those locations that you can see. And those will also have lines of action, right? Which I'll do in yellow. So these are lines that go infinitely in both directions, like you can see there. What we're interested in is finding the perpendicular distance from our point B to those lines of action, okay? And that's called a lever arm, right? We know that to find the moment, we need to multiply the force by the lever arm, right? The magnitude of the force by the lever arm, okay? So we've got an arrow pointing up here, 2 arrows pointing down here, and here's how we're going to do the moment, right? This is just a recap. I'm sure you guys know this fairly well now. Okay, so first let's do the reaction at A, okay? It's going to be negative because that arrow is going to cause a clockwise spin about B, right? Meaning that since we're considering counterclockwise as positive, this is going to result in a clockwise moment and therefore be negative. Okay, so negative AY multiplied by the lever arm of 7.5 meters. Okay, so that's your force magnitude. That's your lever arm. So that's your lever arm. That's your force magnitude. And we're going to do that for every single force that we see here. Okay, so next we're going to add, we're going to account for this force, right? The force due to the dead load. So the force due to the dead load is 31.2, which is the distributed load. But then we're going to need to multiply that over the length in which that distributed load acts in order to find the equivalent point load. All right, so we're going to multiply that by 7.5. All right, so in other words, the magnitude The magnitude is these two numbers multiplied together, right? Okay, and then we're going to multiply that by the lever arm. So the lever arm is the perpendicular distance from that line of action over to our point of reference B. So we're going to do 7.5 divided by 2, all right? So 7.5 divided by 2, that is going to be our lever arm for this distributed load, okay? All right, and then next we're going to account for this force due to the live load, right? So similarly, we're going to do 33 multiplied by the distance in which it acts, which is going to be 7.5 divided by 2, right? 7.5 divided by 2, right? And just like before, that is going to be our magnitude. And lastly, we're going to have to find now this distance here. Okay, so this distance is the lever arm, right, from our point of reference to the middle of the live load. And that is going to be 3/4 multiplied by our overall length, 7.5. It's 3/4 because if you think about it, it's half the beam plus a quarter of the beam. So therefore, it's 3/4 of the beam, right, is the lever arm distance. So that's 3/4 multiplied by 7.5. So that is our lever arm. Okay, so now what you're going to find is that this whole expression is solvable because we've only got one unknown, right? Our only unknown is AY. Actually, it's down here. And AY is going to be 209.8. So we have now just figured out the support reaction A. What we're interested in now is finding the support reaction B. Okay, so what we can do is sum of the forces in the vertical direction, right? And that's going to be AY plus BY are the two forces going up, and the two forces going down are going to be this one. So this is the dead load. Oops. This is going to be the dead load, and this is going to be the live load. Okay. So I'm subtracting both of them because they're both pointing downwards, right? And we know what AY is. It was this number, so we can substitute that out. So now we have an expression which only has one unknown, which is BY. And if we rearrange for BY, we get 147.9 kilonewtons, okay? So now we have both the support reactions, okay? Cool. So this is going to help us draw our shear force diagram. However, we only know this point and this point, right? What we need to do is figure out the point in the middle of our beam, right, in terms of this shear force distribution. How do we find that? We can find that through a linear, oh my god, I've drawn all over it. Okay, a straight line, okay? So imagine this line, okay, and it's mapped shear versus X, okay? So this is a shear force diagram, and we're interested in this line function, and at X is equal to 3.75, right? Okay, so how do we get this straight line function? Well, you'll notice about this straight line function, right? So if we say y is equal to mx plus b, right? V is y, right? Is equal to the gradient, which we'll calculate later, multiplied by x plus b. B is our y-intercept, correct? So b is 209.8. So we know that AY is going to be the same thing as our y-intercept. Okay, so the gradient is what we're going to do next, right? The gradient for distributed loads, right, on a beam. Let me just rub this out. Ah, it's crashed. Has it? Okay. Delete, delete, delete. Okay. So what we're interested in is the net distributed load, right? So basically this distributed load plus this distributed load, right? We're interested in this number, 64.2. Okay, so that distributed load, 64.2, is going to be the gradient of our shear force, right? So that gradient there is the same thing as W star, okay? So that's W star. Okay, and X is going to be 3.75 to get to the middle of the beam. Okay, so when you do this expression on your calculator, you'll find that it is equal to negative 30.9 kilonewtons, all right? So negative 30.9 is the value of our shear force in the very middle of the beam. Does that make sense? So you're just going to need to basically understand how straight line functions work in order to solve for these different parts of the shear force envelope, okay? All right, so yeah, and this is the mirror. So if you were to do the inverse of this, or the flipped loading for that, you'll find this is the shear force diagram. So the shear force envelope basically looks like this. And this is from the first scenario, right? This is from when the uniformly distributed loads applied over the entire beam. And then these values of plus or minus 30.9 come from the loading of half of the beam being live loaded, okay? Whereas the other half is not live loaded. Okay, so what we need to do is we need to basically find a function, again, a straight line function, for this line. Let me zoom in. For this line is what we're interested in now, right? And just like before, right, visualize this as v versus x, right? We're interested in finding this straight line function. The way that we do that is just with y is equal to mx plus b, except here I'll draw it as b plus mx, right? So b is the y-intercept, and the y-intercept in this, for this line, is going to be 240.8, right? So from the first case. And we're going to add on, you can do add, or you can do subtract, right? Depends how you want to do the gradient, right? I'm going to subtract some kind of gradient and multiply it by x. So x is going to be dO, right? We're interested in the position dO away from the support, okay? And how do we find the gradient, okay? The gradient is essentially the rise of a run, okay? So the rise is this, okay? Okay, there's two ways you can kind of look at it, right? You see how this is the bigger number subtracted by the smaller number? That's as if it was the rise going that way. But what I've done is I've done a negative here. So up to you whether you want to do add and then this flipped, right? Or just subtract and then what you see there, okay? So that's the rise over the run, and the run is half the beam, right? And half the beam is 3.75, so that's over 3.75 meters, okay? So now we have an expression for the straight line function, and we've plugged in dO is what x is, all right? And so that gives us a value of 216 kilonewtons, okay? So that's our design shear. Make sense? Kind of? Not really? Right. Similarly, we're going to do the same thing for bending moment, except we don't need to do like any kind of bending moment envelope. The peak bending moment is just going to be from the first loading scenario, right? And what we need to do is we need to find M design, and M design is when you take x is equal to dO. Now the good news is that for a simply supported beam, like you can see here, this has a nice, neat formula, and it looks like this. So you don't need to derive it from the shear force envelope like we did a second ago for shear. You can just use this formula, and this graphs a parabola, okay? And what we can do is we can just plug in these values, right? So dO was 0.445, and L, the overall length of the beam, is 7.5, right? So the design bending moment is going to be 100.8 kilonewton meters, all right? That one's not as bad because we can just plug it into a formula directly, right? Okay, so that's part A and part B of this question. So part C of this question now asks us to design the stirrups, right? So if I scroll on my notes, right, so that's the left-hand side, I want to point out something, okay? So what you'll see is that this formula VU max, right, it's to do with web crushing failure, right? So it's a particular failure mode, but this has been updated in the concrete standards as of later this year. Okay, so Taewan's teaching you what you need to know moving forward, but in your finals, right, and if people have done like final solutions, which you're referring to online, they won't have this 0.9 factor. Okay, so keep this in mind. This is new. All right, this 0.9 factor that you see in this square bracket is new in the new version of the standards that's coming out later this year. And so if you're referring to like, say, a past paper, practice paper from like 2019, right, it won't have this 0.9 in it, okay? So you need to solve these questions with 0.9 moving forward, okay? Does that make sense? Okay. So that's the only thing that's changed. Well, there's two things that changed, right? I'll show you something else that's changed in a later step, right? But in this formula, this is the only thing that's changed. Okay, so essentially we need to work out different parameters in a particular order yet again, okay? So the first one is BV, and as I alluded to before, if you've got a T-beam, right, BV is going to be the web width, okay? I'm changing colors like crazy. So we want 300 mil, okay? We want to put in 300 mil for the shear width, okay? The second one is the internal lever arm, right, for your beam. So that follows these formulas, right? Sorry, this formula, which is the max between two things. It's the max between D, the overall depth, right? And you can get the overall depth by adding the depth of the flange to the depth of the web, right? So you have 510. And the effective depth. So remember, the effective depth is the depth from the compressive face to the middle of the tensile steel layers, okay? Or in this case, middle of the steel layer. Okay, and so that's 445, okay? So you do 72% of this number and 0.9 of this number, and it gives you these two options, and you choose the maximum between them, right? So the maximum is going to be 400.5 mil. Okay, so this particular question, right? This particular workshop question doesn't tell you whether we're going to use the detailed method or the simplified method, okay? So if it doesn't tell you, I would say it's better to do the detailed method, okay? So if the question doesn't tell you to use the simplified method, assume that we're going to use the detailed method, all right? So we need to calculate epsilon x first, all right? So if I scroll down on my notes, okay? So in order to calculate theta v with the detailed method, we need to first calculate epsilon x, all right? So that's this formula. So m star, right, was the design moment, which we calculated a moment ago. Except we have to multiply it by 10 to the power of 6, right, to get it in Newton millimeters. dv we calculated just now. And then v star, again, we got the answer in kilonewtons, but we want it in newtons, right? So we multiply it by 10 to the 3. ES is going to be 200,000 MPa. AST was given to us in the question. And then this gives us a value of 0.00065, and it's less than 0.003. 003, yeah. Okay, and then what we do is we plug in the value, right, into this formula. You're going to see this is the case for, that's basically what I'm going to say for the rest of this workshop. You plug this in and you get this, and you plug this in and you get this, right? It's just a matter of following this flowchart and plugging shit in, basically. Okay, so this gives you theta v is equal to 33.6 degrees, all right? So I'm scrolling down, following this little flowchart thing, all right? And what we need to do is, now that we have all of the values that we need, right, we're going to plug everything into VU max, this formula, okay? Just plugging shit in. Okay, one thing that's kind of important to note is, I mentioned earlier, cot theta v is the same thing as 1 over tan theta v, right? So in your calculator, you can't type cot, but you can type tan, right? The thing is, in this formula, it's going to say cot squared theta v, right? So again, you can't type cot squared into your calculator, but what you have to do instead is type this fraction, 1 over tan theta v squared. Okay, the whole thing's squared. If you think about it, cot squared is just cot multiplied by cot, right? So that's why we need to do fraction multiplication there, okay? So anyway, plug in more shit, okay? All right, and then we get a max shear capacity of 877.2 kilonewtons, okay? And so this value in our capacity equation becomes 877.2. And we checked that this, when multiplied by 0.75, is bigger than the amount of design shear that we're experiencing, right? And yeah, and so once that passes, we can move on to the next step, okay? The next step we're interested in is finding the minimum transverse steel density, okay? So that's ASV dot min over S, okay? So this comes in the form of a formula, and we just do all the stuff that we've been doing before, just plugging stuff in, plugging more stuff in. You get 0.27, so this is the ratio of ASV min over the spacing, right? Okay. So VUC, right, is the next step. So we're trying to calculate the concrete's shear strength now, okay? So we've actually calculated BV and DV already at this point. So all that we're looking for is the aggregate interlock factor, right, KV. So in the previous question, we could actually directly check this because we were given what the stirrups area was as well as the spacing. So we could actually like directly check whether we had enough transverse steel density compared to our minimum steel density, right? Minimum transverse steel density. However, in this type of question where we're doing a full shear design where we don't know what our stirrups are going to look like and how far they're spaced, you need to make an assumption, okay? This assumption means I'm assuming that me in the future, I'm going to design it so that there's enough transverse steel density to meet the minimum requirement, okay? So you have to assume that you're going to do this in a later step, all right? And if this is true, then KV follows this formula, okay? We calculated epsilon x already. It was 0.00065, all right, giving us a KV value of 0.2 if we use the detailed method like we're doing. Okay, and this will inform how we calculate VUC, the concrete's shear strength, okay? Plug everything in, giving us 135.4 kilonewtons, okay? So that's the concrete part done. Oh, sorry, it's not quite the concrete part done because we need to check for whether it passes without any additional steel, okay? So we're just checking the contribution of the concrete by itself and whether it is sufficient to resist the shear forces, okay? So here's the other part which is new to AS3600, okay? It's this factor called KS, right? And it's a reduction factor when you're doing this check, right? So this particular check is checking the design shear against the concrete without any additional steel helping it, okay? So what we need to do is we need to now figure out this thing, right? KS, all right? KS is a function of the depth of your beam, okay? So remember our beam looked like this, right? So it's a T-beam, and the overall depth was 510, right? 510 sits between 300 and 650, right? And so therefore we refer to this middle row, right, when reading off of this formula, okay? And we're going to substitute in D is equal to 510, and therefore KS is going to result in 0.7. So this is saying that it's a reduction factor of 0.7 when we're checking for the concrete's contribution to the strength by itself, right, against the design shear. And what you'll find is that even without the additional reduction factors, the concrete by itself is not going to be able to resist the shear forces, right, that we apply onto the beam. So what we need to do is we need to add reinforcement, okay? So what we we're doing a second ago is concrete, no reinforcement, doesn't work. We need to add steel, we need to add stirrups, okay? So that's step 5, okay? So what you'll see is this looks kind of confusing at first when you haven't seen it before. So in both my notes and what you can see on the screen here, what we're doing is a triple inequality, okay? So on the left, this is saying that whatever value for ASV and spacing, which we're going to select at a later stage, it has to be greater than this whole formula, okay? So this whole formula is essentially like the threshold value for the amount of steel that you're allowed to provide, okay? It has to be greater than this threshold value. And then it also has to be greater than the minimum stirrup density that is allowed, okay, in general. Okay, so let's plug everything in, right? So V star 216, and we're going to get that into newtons again. So remember, this is another formula that's sensitive to units, right? So we need to make sure all of our units comply with those 3 that you see on the screen there. Okay, VUC is 135.4, and you multiply that by 10 to the 3, again giving you an answer in newtons. FSY.F is 500. DV, which is your internal lever arm, is 400.5. And then we plug in theta V into cot, right? Anyway, so once you do this calculation, you'll find that the middle inequality is equal to 0.51. Okay, and now we have to quickly check that against the value that we calculated in step 3, right, which is the minimum that's required, which is 0.27. Okay, so this number is greater than this number, and so we're good to continue to the next step. The next step is comparing these 2 things, right, which is not terribly clear what I'm doing here, so I'm going to add an extra page. Sorry. I'm going to drag that down there. So what this means is we're up to the step where we need to select the stirrup area as well as the spacing. So what this is saying is whatever density that we end up with has to be greater than 0.51. Okay, so this part has to be, yeah, anyway, sorry. This part has to be greater than 0.51, right? Okay, so here's the thing. What we're going to do is we're going to first select the stirrup area before selecting the stirrup spacing. All right. So the stirrup area comes from your table, which informs you of like the nominal area of each of the bar sizes and how many bars you select. Okay. So the important thing to realize is how you go about the logic of selecting various bars. Okay, so let's say this is what your section looks like, right? I know we're dealing with a T-beam, but let's just, for the sake of argument, give you a few examples of rectangular beams, right? So the first thing is, the first type you can do is called double-legged stirrup, okay? So double-legged stirrup refers to a closed stirrup, like so. And it's double-legged because when you cut across this beam, it cuts across 2 legs of your stirrup. So this is a loop, right? And when we're considering the shear area, let's say that the area of the individual bar, let's just say it's a N10, right? 1 bar is 80 millimeters squared, right? But since we're cutting across 2 of them, right, we go 2 multiplied by 80, giving us 160. Right, so this is double-legged stirrup, right? If you want to do a triple-legged stirrup, right, it might look like this, okay? But the thing is, you need enough you need enough longitudinal bars on the top and the bottom side of your beam in order to hook on the stirrups, right? So if you want to do 3 legs, you need at least 3 bars at the top to hook onto, and 3 bars at the bottom to connect to as well, okay? So this is sensitive to what longitudinal reinforcement that you have designed already, okay? And I'll give you another example. Let's say there's 4 bars, right? this would probably be true if the whole thing was a bit wider. Okay, so if you've got a wider beam, you might have more bars, right, to fill in that area, fill in the width, right? And so you might choose to do this. Okay, so two closed stirrups, right? And that results in 4 legs, okay? So this would be an example where you have 4 legs, for example. Or you can do it like, you can detail it like this. Boom and boom, up to you, all right? So anyway, in our case, we're gonna do 2 legs, all right? And we're gonna choose N10s, and so we're going to choose ASV is equal to 160, okay? So once we've chosen ASV, now we're interested in choosing the spacing. So that's going to be governed by this ratio. So if you compare 160 to this number, right, and let's just rearrange the equation to solve for S, right? This is saying that S has to be less than a certain number, and that number is 313.7 millimeters, okay? So that's basically saying you've got your stirrups, right, which we've now chosen the bar area for. The spacing between these stirrups has to be less than this number, okay? Mathematically. However, there's a few designer's choices which you should, I guess, think about before selecting your spacing, okay? I would say that an appropriate number to choose for your spacing is a number between 150 and 250. I would say this is like appropriate range for the majority of design cases, okay? So you'll see later why when we're doing the detailing checks. Oh shit, I just realized we're low on time. Okay, you'll see later why, but I choose to do S is equal to 250, okay? So we're gonna choose S is equal to 250, all right? And that's gonna manifest in this equation when we're plugging in for the shear capacity, okay? Sorry, I'm running out of time, so I'm going to write kind of quickly. All right, so this gives me 192.9 kilonewtons. Okay, so that's the steel's contribution to the strength. All right, based on the area and spacing of the shear bars that we chose, right? Okay, so what that means is we can plug in 192.9 into this check, giving us 246.225 kilonewtons, all right? So on the right-hand side of this equation, that is 246.225 kilonewtons, right? Compared to the left-hand side is 216, right? And 216 is less than this, and therefore it's okay, right? So our beam's not going to fail. So what you'll notice is that in the previous step, when we were checking for just the capacity of the concrete without any steel, we needed to apply this reduction factor of Ks, right? But when we're doing it where you have steel and concrete acting together, you don't need to apply that reduction factor of Ks. So Ks, again, is new to the standards as of later this year, okay? So for your minimum design checks, I'm just going to run, I'm going to switch over to my master copy, just in the interest of time, right? There's 3 checks we need to do, okay? There's your spacing check. So I'm going to scroll down here, okay? So on the left screen, what you'll see is that's my notes, right? And the spacing check depends on your beam size, okay? So if your beam is less than 1200 mil deep, right? As is the case for us, where our beam is 510 deep, then our spacing has to satisfy these 3 values, right? The first value is 300 mil, okay? So remember, before, our inequality told us that our max spacing was 313, right? But right off the bat, that's going to be invalid because AS3600 requires the max spacing between stirrups to be 300 mil. So that's the first check. The second check is it has to be less than half the beam's depth, okay? The beam was 510 deep, and so half the beam's depth is 255. So luckily we chose a spacing of 250, and that's less than 255, so that's all good. The other one is capital S max, right? Capital S max has its own formula, and when you plug everything in, you'll see that that's equal to 580 or something like that. Anyway, so a lot of the time that doesn't really apply. It's not going to govern, but you still need to check for it, because usually this number is going to be bigger than 300 and the other one anyway. Anyway, so the spacing that we chose was 250. So it satisfies the three spacing requirements, right? The governing one was 255. The other thing is we need to check for web crushing, right? So the ultimate capacity of the beam, that's the concrete contribution as well as the steel contribution, has to be less than what we calculated for the web crushing failure mode, right? Which was 877.2. Okay, and then lastly, we need to check that our minimum stirrup requirement was satisfied. All right, so the area of steel we chose for our stirrups, right, divided by its spacing, is greater than the minimum that was required based on that formula that we used, right, which ultimately gave us 0.27, right? So 0.64 is greater than 0.27, right? And so therefore it's fine. That's the end of the question. All right. Thank you very much for joining. And thank you very much for joining. Okay.